This is Cooper Riley, and my optimization problem has to do with rockets and how big they need to be, depending on what they're launching into orbit. The space industry is still relatively young and has been dominated by government programs, launching rockets of varying sizes for many decades. Recently, however, the private sector has been growing quickly, starting so far with cargo transport and eventually moving into human transportation. The work done by the government is invaluable to these newcomers, laying the ground rules and defining many of the terms and equations critical for spaceflight. The most important factor in launching a rocket is to know it will be able to make it to orbit, of course. This is dependent on the mass of the rocket, its payload, and how much fuel is on board. My model is simplifying a rocket down to its outer dimensions, its height and its diameter. These determine the weight of the rocket body and the amount of fuel that it can carry. There's also a payload at the top, which adds to the weight of the rocket while not increasing the fuel capacity. This can be varied between optimization runs to determine the optimal rocket size for a given payload. The most important bit of rocket theory I'm using is called the ideal rocket equation. It calculates the amount of delta V available in a vehicle based on the ratio between its launch weight and its weight after burning all of its fuel. Essentially, it tells you how much you can speed up the rocket based on how much fuel you have to throw out the back. This model does not take into account more complex interactions between the rocket and the atmosphere. It is more of a tool for reference in determining rough dimensions for a given application. My optimization strategy was to use the fmin function in MATLAB. My fitness function is just the total mass of the rocket at the time of launch. That's the body of the rocket plus the weight of the fuel plus the payload. The idea being if you can minimize the mass, that then reduces the cost of the materials, which then gets us the most efficient use of our money. Our design variables are just the height and diameter of the rocket, which then determine the amount of fuel and therefore the weight of the rocket. The constraints are the delta V calculation, which is dependent on the design variables, and the payload, which will be sent and can be set before each optimization run. Of the initial results, the initial trials, I tried using an additional design variable, which would have been the percent of the rocket volume which contained fuel. This was getting strange results, so I eventually tried a new assumption where the structure would just be 10% of what I was using before, the idea being it would be a truss structure rather than a solid block of material for the body of the rocket, and that helped bring my results in line. I also tried using a fitness function with an added penalty term. This is what incorporated the delta V instead of using MATLAB's nonlinear function capability. So it produced similar results but added a lot more complexity to the script, and once I figured out the 10% structure rule, I went back to using the nonlinear function. Finally, here are my results. Here the design space has the height and the diameter on the x and y axes. The contours are our fitness function, the mass of the rocket, 0 down in the origin and increasing up to the right. The red lines are the constraints. These two are aspect ratio constraints to make sure our rocket isn't too short and fat or tall and skinny. And the curve is the delta V constraint, which is what we're most concerned with. In these runs, the delta V is set to be at least 9.4 kilometers per second, which is what's needed to get into low Earth orbit. The chart's running with a payload of 50 kilograms, about 110 pounds, maybe a small satellite if you wanted to send one up. Since we wanted to have the lightest rocket with enough delta V, it makes sense to see our result right on the edge of this constraint. These aspect ratio constraints can also be adjusted depending on launch conditions, such as maybe your launch facility has a bottleneck and you need the rocket to be no wider than some value or no taller than some value. Here's some additional runs. Say if you had a payload of 90 kilograms, about 200 pounds if you wanted to send up a friend in some breathing equipment, maybe. 5,000 kilograms, maybe a larger satellite, looking for a rocket of 30 meters and 3.1 meters in diameter. How about the Hubble Space Telescope, weighing in at about 11,000 kilograms? You'd need a rocket of about 40 meters tall or 4.5 meters in diameter. Rockets such as the Falcon 9, which are used today, are 70 meters tall by 3 meters wide. And in that case, they need extra fuel to make a landing. So I feel that these results are fairly consistent with real-world application and in rockets that are in use today.